Let's take a look at the normal approximation to the binomial distribution. The continuous normal distribution can sometimes be used to approximate the discrete binomial distribution. Why would we want to do this? In the olden days, it was very useful for probability calculations. The binomial formula can be a bit of a pain if it has to be used over and over and over again, and so this normal approximation came in to make lives much easier. These days, the computers can do the calculations for us, so it's not as much of an issue there. But we still use this normal approximation in statistical inference. When we do things a little bit later on, like statistical inference for proportions, we often use this normal approximation, so it's good to know a little bit about it. Now, you may recall that the binomial distribution is perfectly symmetric if p is exactly equal to 0.5 and will have some skewness when p is not equal to 0.5. Now, the normal distribution is a symmetric distribution, and so the normal approximation is going to work best when p is close to 0.5, and it's going to work better and better as we get a larger and larger sample size as well. For illustrative purposes, here is the binomial distribution with n is 40 and p is 0.5. And as you may be able to tell, this is a perfectly symmetric distribution in this case. And let's say we were to superimpose a normal curve over this distribution. It looks awfully normal. That superimposed normal curve fits pretty well. And we'd see that if we jacked up the sample size even higher and higher and higher, that normal curve would fit better and better. Now, what if we're a little bit closer to the boundary here? Here, p is 0.03, which is close to the boundary of 0, and we've got the same value of n, but we see a little bit of skewness. And if we were to superimpose a normal curve, it does not fit very well. If we amped up the sample size larger and larger, we'd see that the normal approximation is going to be better and better as that sample size gets larger and larger. But the general idea here, when we get near the boundaries of 0 or 1, we are going to need a larger and larger value of n for that normal approximation to be reasonable. And this idea is summarized in this rough guideline, that the normal approximation is reasonable if both n times p is bigger than or equal to 10 and n times 1 minus p is bigger than or equal to 10. And if you play around with that a little bit, you'll see simply that if p is close to 0 or 1, we need a larger value of n in order for the normal approximation to be reasonable. Now, this is just a rough guideline. Sometimes people replace 10 with 5 here, and sometimes they use different rules altogether. So you should consult with your professor or your textbook to see what rough guideline they are using. Recall that if x is a binomial random variable, then x has a mean of n times p and a variance of n times p times 1 minus p. And what we were just discussing above is that x can be considered approximately normal in certain settings. And so then we can standardize this in the usual way. We can say x minus mu over sigma, using mu from up here and sigma being the square root of sigma squared from here. Then this quantity we're going to call a z. And we're going to call that z because that quantity has approximately the standard normal distribution. So my z is going to be approximately standard normal. Normal with a mean of 0 and a variance of 1. And now we're going to use this in probability calculations. So let x be a binomial random variable with n of 75 and p equal to 0.6. What is mu? Well, we know mu is equal to n times p, and that's going to be 75 times 0.6, and that works out to 45. What is sigma squared? N times p times 1 minus p, and that is going to be equal to 75 times 0.6 times 1 minus 0.6, and that works out to 18. And so our standard deviation is simply going to be the square root of 18. Now, suppose we wanted to use the normal approximation to estimate this probability. We could calculate the exact probability from the binomial distribution using a computer or even by hand if we had to, but we're going to use the normal approximation here. And we're going to say that the probability that x is bigger than or equal to 52, this is going to be approximately the probability that z is bigger than or equal to, we could say, 52 minus the mean, 45, we're simply standardizing like normal, divided by the standard deviation, square root of 18. And this is equal to the probability that z takes on a value that's at least as big as 1.645, rounded to 3 decimal places. Then we would go to a computer or our Standard normal table. Here's 1.645, and we're interested in this area. So I'm going to leave that up to you to verify for yourselves that that's going to be approximately 0.0495. If you use a standard normal table instead of a computer, you might get a rounded version of that, but you should get pretty close to that value. Now compare that with the exact value that we get if we use the binomial formula, which I'm not showing here, but I used a computer to get the exact value based on the binomial distribution, and we get 0.0611. And our value based on the normal approximation, well, it's in the ballpark, but it's still a little bit off. But we can improve that approximation with something we call a continuity correction. We are moving from this discrete binomial distribution to this continuous normal distribution, and when we do that, we can improve the approximation with this continuity correction. To illustrate, let's look what's going on here. This is a plot of the binomial distribution with n is 75 and p is 0.6, and the shaded green part is the probability that we're interested in, the probability that we get a value out of 52 or greater. Now what if I superimpose the normal curve? Here's the superimposed normal curve, and this red shaded area is the probability calculation that we carried out on the last page. And here is the value 52. Now, in the binomial setting, 52 means something. 52 successes out of 75. But on the continuous front, for a continuous random variable, 52 means 52.00000000, infinite zeros there. And it is distinctly different from 52.00000001, say. Now I've blown this part up on the next slide just to make it a little easier to see. So to come closer to regaining our original meaning of 52, we're going to say, okay, 52 in the discrete sense had some meaning. 52 in the continuous sense means exactly 52, 52.00000. So to regain that original meaning, we should let 52 take on all values between 52.5 and 51.5. That way, it comes closer to representing what is intended here in the binomial distribution. And so as we can see here, right at 52, when we started at 52.0000 and we did our probability calculation, we were really missing out an important part. We were missing out this half of 52 in a sense. And so what we really should do is start here at 51.5. That's where we should start. So that's what it looks like on the next page. If I start at 51.5, my approximation, my red shaded area here, is going to be a lot closer to the total of those green probabilities and a lot closer to reality. So if I want my probability that x is bigger than or equal to 52, before doing the normal approximation, I am going to use the continuity correction and say this is the probability that z is bigger than or equal to 51.5 minus the mean over the standard deviation. This works out to the probability that z is bigger than or equal to 1.532, and we go to our standard normal table or a computer or what have you, and if we did this without any round off error and just rounded our final answer to 4 decimal places, we'd see that this is 0.0628. And as I'll illustrate in a little bit, that's closer to the true probability based on the binomial distribution than when we didn't use the continuity correction. In this new question, we're interested in the probability that x is strictly greater than 52. That is what the shaded green bits represent. And to be strictly greater than 52, I want to make sure I don't include any of 52, so I really should start right here. I should start at 52.5. Let's see what that shaded area under the normal curve looks like. That looks a little bit better. And so I want my probability that x is strictly greater than 52. This is going to be approximately the probability that z is greater than 52.5 minus my mu, which is 45, divided by the standard deviation, which is the square root of 18. This works out to the probability that z is greater than 1.768. And if we found that value under our standard normal curve, 1.768, and we did it without any round-off error and rounded our final answer to 4 decimal places, we would see That's the answer. Now you should be able to come close to that, but not exactly that, from a standard normal table. Now what about here? Let's say I wanted the probability that x is less than or equal to 52. That's what that shaded green bit represents. And I can't start exactly at 52. That wouldn't be quite right. To include all of 52 and go left, I need to start here. I need to start at 52.5. So let's see what that looks like when shaded under the normal curve. That looks like it might provide us a pretty reasonable approximation. So when I want the probability that x is less than or equal to 52, that's going to be approximately, with my continuity correction, I want to include all of 52, and so I should start at 52.5. Subtract the mean, which is 45, and divide by the standard deviation. This is going to be equal to the probability that z is less than or equal to 1.768. And if we plot that out, 1.768, that's this entire area here. And that works out to 0.9615. What about if we're interested in the probability that x is strictly less than 52, which is represented by the green shaded bit? If I'm going strictly less, and I don't want to include 52, then I should start here at 51.5. Let's see what that looks like when shaded in. That looks like that might give us a pretty darn reasonable approximation. So if I want my probability that x is less than 52, then I'm going to say that's approximately the probability that z is less than 51.5 minus mu over sigma. And this is equal to the probability that z is less than 1.532. And if we put that into our computer, and we did this without any round-off error, and then just rounded to 4 decimal places at the bitter end, we would say that this is 0.9372. So let's look at a summary of what we just did. If I want the probability that x is bigger than or equal to 52, then I want to include all of 52 and go right, which means I should start at 51.5. If I want the probability that x is strictly greater than 52, well, I'm going right, but I don't want to include any of 52, so I should start at 52.5. If I am going left, less than or equal to 52, I want to include all of 52 while going left, which means that I should start at 52.5. And if I'm going strictly less than 52, I want to make sure I don't include any of 52 while going left, which means I should start at 51.5. Now, I strongly recommend that you don't simply memorize this, but that you try to follow the underlying logic. If you truly understand why we're doing what we're doing here, then it'll be easier to do properly when you have to. Now let's take a quick look here at how that continuity correction improved the approximation for a couple of cases that we just looked at. If we're interested in the probability that x is bigger than or equal to 52, without the continuity correction we got 0.0495. But with the continuity correction we got 0.0628, which is much closer to the exact value based on the binomial distribution. That's what this exact value is coming from. Similarly down here, when we wanted greater than 52, we had 0.0495. We used the same calculation in both cases. We didn't use our continuity correction. And with the continuity correction, we get 0.0385, which is much closer to the exact value based on the binomial distribution. So the continuity correction has greatly improved our approximation.